In this video, we'll look at the waveform of FM and PM. Before we do that, let's look at the definition of PM and FM again. If we look at the PM, if I replace the message, this definition, by this definition, by the integral, we can see PM become FM. Now, if I look at the derivative of phi, I have this relationship for PM. That's Kp derivative of mt. For FM, I have 2 pi kf mt, which I take the derivative of phi from the definition of phi of t for FM, for PM and FM. Now, if we look at this term, if I look at the FM, if I replace FM by the derivative of the message, then FM become PM. So we can see for FM, PM, they can really interchange, and therefore FM and PM are both called angle modulation. And we're going to analyze one type of the modulation. We normally analyze FM. The results and the analyzing strategy applies the same for PM. Next, let's look at the examples. In this example, we look at this message. I call it message 1. Message 1 has this shape. It's rectangular. It equals to 1 from time 0 to 2 seconds, and from 2 to 4 seconds, the value of the message becomes -1. Now I'm going to use FM modulation. The FM modulation has this format. So AC cosine 2 pi of CT plus phi. Phi equals 2 pi KF. I do integral from -infinity to T of the message. So this is a definition of FM we want to know. Now we derive the instantaneous frequency. Fi equals FC plus KF mt. If we choose KF equals to 10, KF is normally given for FM modulation, then we can say when mt equals to 1, the instantaneous frequency equals FC plus KF, that's equals to FC plus 10. And then for mt equals to -1, the instantaneous frequency equals to FC minus KF, that equals to FC minus 10. So now if we want to plot the waveform of the modulated signal for FM, so this is the modulated signal U of t that equals to this. When mt equals to 1, the time is from 0 to 2. The frequency is FC plus 10. So that's a cosine signal. So we have higher frequency here. So the magnitude is AC. So this is AC. This is a minus AC. For time 2 to 4, the frequency decrease. The frequency is FC minus 10. So it's lower frequency now. This is just illustration purpose. The frequency you can see here from 0 to 2, I have higher frequency for FC plus 10, and from 2 to 4, this is 4, I have lower frequency, that's FC minus 10. So I plotted here 0. This is a 2. And this is a 4. And from 4 beyond, the frequency, the message signal is 0. So actually it goes to FC. The frequency goes to FC. So this is FC plus 10. This is FC minus 10, and this is FC. This is our, for illustration purpose, so this is our time t. Now let's look at another example. I call it message 2. This is a triangular waveform. So from 0 to 2 seconds, the message equals to t. And here, this is 2. And from 2 to 4, the message is equals to 4 minus t. Therefore, at time 4, mt equals to 0. At time 2, the message equals to 2. In this example, we're going to use PM, the phase modulation. The phase modulation, we have this definition, AC cosine 2 pi plus phi, but phi is equals to kpmt. In this case, I'm going to choose kp equals 2 pi multiplied by 10. That equals 20 pi. This equals 20 pi. Because of our message, it has different waveform for different section of time. So we can write the modulated signals according to different time frame. So from time to 0 to 2, the message equals to t. So that's equals 20 pi multiplied by t. And in the time from 2 to 4, the message is equals to 4 minus t. So 4 minus t. Plug in here. If we want to plot the waveform of the modulated signal, we need to know the frequency. To obtain the frequency, we take the derivative of the angles divided by 2 pi. At t from 0 to 2, the instantaneous frequency, we take the derivative of the angle, take the derivative of this angle and divide it by 2 pi. So 2 pi d of dt, that's this portion. Here you can say 2 pi cancel out each other, and this has become 10, and that equals to Fc plus 10. Now for time from 2 to 4, we have the angle of this portion. So we plug it in, 2 pi cancel out each other, this become 10. And you take the derivative of 4 minus t, that's minus 1. And this equals to Fc minus 10. Instantaneous frequency is Fc plus 10 for t from 0 to 2, and Fc minus 10 for t from 2 to 4. And if we want to plot this waveform, we got exactly this. This is Fc plus 10, from 2 to 4, Fc minus 10. And from beyond mt equals to 0, mt equals 0, phi of t here is equals to 0 now. So the frequency beyond this 4, that's Fc. From these two examples, we can see FM and PM, they really can share the same waveform of the modulated signal, but the message is different. You can see this message is the derivative of the second message. If I take derivative of this message here, I got 1 and minus 1, right? And if I take the integral for the first message, that's rectangular, I will get triangular. These two examples illustrate the relationship between FM and PM. So if a message is the integral of another message, so FM become PM. If a message is a derivative of another message, then PM become FM.